Next in person, we have a cryptoeconomic traffic analysis of Bitcoin's Lightning Network by Ferenc.
Hello everyone, I am Ferenc Béres from the Hungarian Institute of Computer Science and Control. I am a PhD student in network science, so today I'm going to show you how we use network science to make some valuable insights related to the Lightning Network. As you know, the Lightning Network was designed to solve the scalability issues of Bitcoin. Its participants can issue off-chain payments to the nodes that they can reach in this network. For simplicity, you can think of it as the abacus game when you move the coins between channel endpoints every time a payment occurs. The number of coins on each edge represent its capacity. To see the Lightning Network in action, let's take a toy example when Alice wants to send a payment to Carol. Due to the observed state of node capacity balances, she must route her payment through Bob here. But in exchange for routing, Bob will charge her with a fee that has three components. Well, the value of Alice's payment, as well as the base fee and the fee rate that was set by Bob individually. The financial incentives of Bitcoin miners is a well-researched area, but according to our best knowledge, there is no similar work for Lightning Network routers. So that is why our main objective was to somehow quantify and measure the profitability of Lightning Network routers at the current state of the network. Because, of course, they play a key role in the Lightning Network. Thanks to Antoine from Coinmetrics, we had channel data from the earliest days of the Lightning Network. In the first few months, you can see a slow network growth, which is followed by a rapid increase in the number of channels as well as the total network capacity. After this shift in November, the increasing average degree and the decreasing distance between most node pairs, which is namely the effective diameter, characterizes the pace of the network densification. We also investigated triangle closure, which is an expected behavior for social networks like Twitter and Facebook. For these networks, in case of two friendly connections, it is quite probable that the third node pair would also be friends. But what do you think was the case for payment channel networks? Well, if you think about it, one would not expect this behavior, because if Alice and Carol can route payments through Bob, then why would they open a direct payment channel between each other? Surprisingly, we found that after measuring the distance, the path distance between every channel endpoint, we found that most of the channels indeed close triangles. So it is a very interesting behavior. According to our opinion, the high number of closed triangles could indicate problems in payment routing, and it can also indicate that there are imbalances in individual node capacities. Due to time constraints, I cannot tell you more about Lightning Network temporal analysis, but you can find our related experiments in the paper. Now, I will move on to our main contribution, which is a Lightning Network traffic simulator. We use this tool to investigate two important questions: the financial motivation and the incentives of the routers, as well as the privacy provisions of the whole network. After validating simulator parameters on publicly available routing income data, we investigated the following questions. Maybe the most important of all is how profitable are Lightning Network routers at the current state of the Lightning Network. But we also investigated whether they are over-provisioning their channels, and of course, what is the payment failure ratio. As for privacy provisions, we studied how easily can they de-anonymize the payments, which is somehow related to payment pass length distribution. In order to answer these questions, we needed to mimic the daily flow of payments on the Lightning Network. But unfortunately, the real payments, as well as individual node balances, are hidden from us. These are private data that we cannot use. So one cannot do more than to rely on the publicly available network structure and the transaction fee data, which was available to us in the form of daily Lightning Network snapshots. Now let's try to understand how our simulator works. For each snapshot, we generate tau random payments with the same constant payment value in satoshis, which is denoted by alpha. The sender nodes of these payments are sampled uniformly at random from all Lightning active nodes, while for the receivers, we include external information on Lightning Network service providers. We managed to collect more than 100 merchant addresses from the 1ml.com website in early 2019. Basically, our idea is that with high probability, we will sample receiver nodes from this merchant set, while we also sample random receivers with small probability from the whole node set. If you think about it, our approach tries to imitate that people spend most of their money at service providers. So this is the basic idea behind the simulator. Between each payment sender and receiver node, we apply cheapest path routing with respect to the latest state of channel capacities. And after each simulated payment, we will update individual node balances for the nodes that were involved in the latest payment. We also managed to validate our approach using publicly available routing data of the alembic.com entity. This is a very important entity because in early 2019, it owned more than 50% of the total network capacity with approximately 25 active nodes. In a blog post, this entity stated that on a daily basis, he only earns a few thousand Satoshi routing income by routing a few hundred payments. So that is why we were tuning the simulator parameters over multiple days, several times, to meet the same ranges of routing income and routed traffic for the nodes of alembic.com in the simulation. In the ping box, you can see the best parameter set that we found. Namely, it is a few thousand micropayments every day, where 80% of the receiver nodes will be from the merchant set. And here comes the magic. Using this validated parameter set, we managed to estimate daily routing income and traffic for every Lightning network entity. Due to space constraints, you can only see the top 4 entity with highest estimated income. But in our paper, you can see the same statistics for more than 20 relevant router entities. Dividing their estimated annual income with the amount of satoshis that they bound in the form of network capacity, we try to estimate their annual return of investment. Surprisingly, we found that there was only one entity, romper.com, who achieved higher than 5% annual return of investment. But if you look closely, Rompert has a very good recipe for that. He charges high fees. He also have high estimated daily income, and he bound just a moderate amount of network capacity on his channels. So it is a very good recipe. It is fascinating to see that despite high fees, he could still achieve a high daily estimated traffic. But if you think about it, it might indicate that this node indeed optimized its position in the network. Unfortunately, if other nodes want to reach this economically high 5% annual return of investment, then they need to increase their routing fees significantly, sometimes even to the range of on-chain transaction fees, which is approximately a few thousand satoshis. But here comes the problem. If every entity would charge these economically high fees, then the negligible fee core value proposition of the Lightning Network would no longer hold, and general users would have less motivation to send their payments over Lightning. According to our measurements, the main problem here is the immature Lightning Network fee market. As you see, from the data we observed that more than 60% of the nodes charges the default value of the base fee and the fee rate, while they may over-provision their channel capacities. So that is why we conducted an experiment where we were gradually reducing the amount of capacity borne by the entities, and we observed the decrease in daily income in the process. Incorporating these changes into the return of investment formula, we found that several entities would need to keep only a small fraction of their original capacity to reach optimal return of investment. For example, for lmbig.com, we found that this entity would achieve more than 20 times higher return of investment only by keeping 1% of its original capacity. Now let's talk about some future prospects. Due to the continuous growth in the network size, one would expect orders of magnitude higher payment traffic for the future. So that is why we were experimenting with different values of traffic, as well as with different values of payment, because as more and more merchants are introduced into the Lightning Network, the range of products available would be much wider, and maybe the price would also change. For each parameter setting, we measured the payment failure ratio for the simulated payments. And surprisingly, we found that for increased values of traffic and increased payment value, the payment failure ratio would increase almost by 10% compared to the estimated state of the Lightning Network in 2018. So, what does it mean for the routers? Well, it means that if they would like to meet the increased future traffic, then they would also need to bind additional financial resources in their channels if they want to transfer and route the payments in the future as well. And bounding additional financial resources may reduce their profitability even more. Now I'm going to talk about payment privacy. But first, let's see a toy example. In this example, Alice sent a payment to Bob through a single router entity. Due to onion routing, which is the key privacy feature of the Lightning Network, this entity cannot be sure whether the payment came from Alice or just a neighbor of her. And it is the same for the receiver end as well. But once the entity takes into account the payment value, then it could eliminate channels that have less capacity than the payment value, because these are the channels that couldn't be used for transferring this payment. And in this case, this entity would have a much better guess at the true payment sender and the receiver. So now you feel that the anonymity set of the Lightning Network nodes is comparable to their degree with a given capacity threshold. So that is why we were measuring Lightning Network degree distribution for different capacity thresholds. And from our measurements, you can see that there are a lot of nodes with low degree and with even lower capacities on it. So it is extremely bad for payment privacy. Using our simulator, we also measured that more than 70% of the payments had only single or two intermediaries. On the diagram, you can see the payment path, but of course it is one intermediary and it is two intermediaries in the payment path. And as you remember, a simulator uses cheapest path routing. So and now you can see the real problem for cheapest path routing, which is the majority of short payment paths. I would like to note here that there are already solutions that are much smarter, and they apply a much smarter routing algorithm than cheapest or shortest path routing. For example, there is a similar solution in the C Lightning client as well. But in this work, we also propose another solution using a genetic algorithm. Our goal here was to find cheap paths that has at least a given amount of, or given number of intermediaries in the payment path. Now, I would like to show you a small example, and I will show you how our genetic algorithm works for this example. Well, in this case, there is a payment path with a single intermediary, and we would like to correct this short path to have at least two intermediary nodes. Well, in the first step, we will generate hundreds of random payment path candidates with random node insertion. And over multiple iterations, we try to merge the cheapest path candidates into new, maybe even cheaper candidates. And in the end, we will return the cheapest among all path candidates. So if you have a look at it, this is how genetic algorithms work in general. Fortunately, our results showed that the mean payment cost as well as the median payment cost only increased by a negligible factor using our solution. So on the left side of each plot, you can see the mean payment path for the cheapest path routing, and after multiple steps, we increased the required minimum number of intermediaries, and the increase was negligible in the cost. So fortunately, our solution can increase payment privacy while still keeping the costs in the range of the cheapest path routing. Okay, now I would like to conclude. As you saw, our payment simulator has a lot of useful cases. Well, the first of all is you can estimate routing income and routed traffic amount for every Lightning Network node. You can optimize channel capacity with respect to the return of investment, and you can also optimize no transaction fee, which unfortunately due to time constraints I could not address in this presentation, but you can find the details in our paper. I already mentioned genetic routing, which can find cheap paths that has multiple intermediaries, and finally you may generalize these results to other payment channel networks. Our tool is available on GitHub, and we have just added a brand new documentation for the code in the recent days, which I hope will be useful for this community. Thank you for your attention.
Do we have any questions from the audience? I have one, and I guess it's all moderators asking the questions. So my question was, did you consider optimizing for all three of the points in that final slide, like maybe sort of as a way of setting the defaults within the clients? You know, minimize the amount of value that the routers deposit into the network while maximizing privacy?
Yeah, I think a combined approach would be much better, but we were investigating these points only by themselves. So we separately analyzed these points, but actually our simulator could be much more efficient if we could combine these factors as well, and if we could optimize for that. So it's a very good idea. Thank you.
Thank you.
So you spoke about genetic algorithms,
Yeah.
and when you're using genetic algorithms, you usually have a number of parameters or different variables, like the elitism and mutation and number of iterations you go through and things like that. So how did you choose those parameters, or did you take a combinatorial approach?
Yeah, actually, we were taking into consideration the running time. So maybe these results wouldn't be optimal, because as we increase the number of required intermediaries, then the running time would also increase. Actually, we were just experimenting with a few hundred random candidates and maybe just 5 or 10 iterations.
Okay, last question over here.
I had a question on, there's a chart that showed the daily returns and the daily amounts. What units was that in?
Daily, the table, right?
Yeah, there was a table on that's showing, yeah. So
Yes.
you see the daily income. What are the units of those numbers? Like take the number 158,119. What unit is that?
Yeah, it is. So you are asking for this?
No, you see it says daily income?
Yeah, the capacity is in satoshis, millions of
daily income
Yeah, it is also in satoshis.
in satoshis. Okay,
Yeah.
thank you.
Okay, in the interest of time, we're going to wrap up there. So thanks very much, Ferenc. Thank all the speakers from the session, please.